We're going to explore how to solve three equations simultaneously in a manner that's very similar to the way we can solve two equations simultaneously. We're going to try to eliminate variables one at a time and pare it down to one equation with one variable. This works differently than with two equations in a little sense, because what we're going to try to do is take three equations with three variables and turn it into two equations with two variables, and then use our two equation, two variable process to finish the problem off. So to do that, what we do is pair the equations up. We can take any pair of equations and eliminate one of the variables. So since z is has a coefficient of 1 in each case, let's eliminate z, or actually let's eliminate y, because the y in the first equation and the y in the second equation are of opposite signs. So if we simply add the first and second equations together, we get the result of 3x plus 2z equals 11. Now, what we want to do is use either the first and third equation or the second and third equation. In other words, the third equation with one of the other ones, and also eliminate y to get an equation that has two variables in it. Then we can do our standard two equation, two variable method for eliminating either x or z, and we're down to one variable and one equation. So to do this, however, we look at it and we realize that the y's have a different amount. So we're going to take the second equation. We're going to take this second equation and we're going to multiply it by 2. That's going to yield 4x minus 2y plus 2z equals 8. And of course, we'll just rewrite the third equation again. That's 3x plus 2y plus z equals 11. And now, of course, since we have an opposite number of y's in the two equations, when we add the equations together, we're going to get 7x plus 3z equals 19, and the y's are gone. Now we have two equations in two variables, and we can use our standard procedure to solve it. In other words, we're going to take this equation, I've just rewritten it down here, and we can use our standard procedure to solve this, which is to look at it and say, if I multiply the top equation by 3 and the bottom equation by -7, I'm going to get the following two equations. 21x plus 9z equals 3 times 19 is 57. And on the bottom, I'm going to get negative 21x minus 14z equals negative 77. And now I'm prepared to eliminate the x's, since they have the same number but opposite value. When I add these two equations together, I get 9z minus 14z, so be careful with your signs. That's minus 5z. And when I add the numbers together, of course the x's are gone, so it's just negative 5z equals 57 minus 77 is negative 20. Divide both sides by -5, and of course we get z equals 4. Now, to finish this problem off, we would go back to either of the two equations that we had produced with only x and z in it, substitute z, solve for x, then we have both x and z, and we take those answers and substitute into any of the original equations to find what y would be. Of course, we could do this to eliminate x's or eliminate z's from either of these, any of these equations, and just simply solve for x and y that way by eliminating z or the other variable. So we'll look at a second slide where we'll actually practice eliminating the x's and then eliminating the z's and coming up with what y is equal to. So let's use this same set of simultaneous equations to eliminate x for some practice. If we come along and recognize that if we double the top equation, if we multiply it by -2, and the reason we want negative is so that we get opposite signed values of x, we're going to get -2x minus 2y minus 2z equals -14. And we'll rewrite the second equation directly under it so that we can add them together properly. Plus z. So much of these problems is about good bookkeeping. So find a careful way to do it. Now we notice I've circled the x's. They will eliminate each other when we add these two equations together. We're going to get -3y minus z equals -10. We'll look for some way to do the second and third equations, and what we're going to do is challenge ourselves just a little bit more. We're going to multiply equation number 2 by -3, and we're going to multiply equation number 3 by 2. So we have to multiply each equation by something, and that's going to yield -6x plus 3y minus 3z equals -12. And on the bottom equation, we're going to get 6x plus 4y plus 2z equals 22. And as we've seen before, we can now eliminate the x's, and we will get 7y minus z equals 10, excuse me. That's a 12 over here. What that's going to allow us to do now is add the first equation that we produced to the opposite of the second equation. So if I rewrite those two equations, the first one is going to be -3y minus z equals -10, and the second one is going to be -7y plus z equals -10. I've done that by multiplying the second equation that I produced times -1, so that the z's will now eliminate. And what I get when I add those together is -10y equals -20, which of course means that y equals 2. Now that we know that y equals 2, from before we produced that z equaled 4. So now we have z equals 4, y equals 2, and if we plug those values into any of the other original three equations, if we do it on the top one, it's obvious that x is going to be 1 then, because z plus y is 6, and there's only 1 left over to add up to 7. And you can double check for yourself that if you plug those into either the second or third equations in the original three equations, you will find that that makes each equation true. This set of answers with x equaling 1, y equaling 2, and z equaling 4, plugging them into any of those three equations makes them true.